So now that we've visualized Java futures, let's go ahead and show how you can apply them in practice. And we're going to use this kind of following on to the example we just visualized to demonstrate how to multiply big fraction objects concurrently using Java futures and the Java executor service framework. So we're going to work on something called a big fraction. Big fraction is a class that gives you arbitrary precision fraction arithmetic. And the way it works under the hood is it uses big integers for numerator and denominator. For the big fraction, big integers can hold arbitrary precision. Numerators and denominators, they can be arbitrarily large up to the point where you run out of memory on your machine. And you can do various things with this. You can have a bunch of factor methods for creating reduced fractions, where a reduced fraction, something like 12 24ths is 1/2, or 44 55ths is 4/5, or 144 216ths is 2/3, and so on and so forth. And then there's also factor methods for creating non-reduced fractions and then reducing them. So there's methods for reducing a fraction that may be non-reduced. There's also methods that do arbitrary precision arithmetic, like multiplication, division, addition, and subtraction, like I'm showing here, where 18/4 times 2/3 equals 3. And then you can also create a mixed fraction from an improper fraction. So if you have an 18/4 improper fraction, you can convert that into a mixed fraction, which would be 4 1/2. So let's take a look at how we can use Java futures to do big fraction arithmetic. And we're going to do this by using a callable, which we talked about before, and the common fork join pool. And you can see down here, this is part of my EX8 folder in my GitHub repository. So we start out with some big numbers. You can see F1 and F2 are large fractions, and we create a callable, which is a two-way task. It's a functional interface in Java 8 parlance that will return a result via a single method that takes no arguments, but you can pass in arguments here using essentially the concept of immutable or effectively immutable variables. We can initialize this using supplier lambda syntax, which is good old Java 8 functional programming. So we can say the callable is a supplier lambda that will create two big fractions from the strings that are effectively final, and then we can go ahead and have those things multiplied together. So F1 and F2 are these effectively final variables. Down here, we then take this task and we submit it to the common fork join pool, and that will then run that task in the common fork join pool when there's nothing else ready for it to be run. What you get back when you invoke the submit call, we invoke submit, we get back a Java future to the results of that computation. And then other stuff can take place. So we could go off and interact with the user. We could invoke other operations to run asynchronously or whatever we want to do while that big fraction multiplication is taking place in the common fork join pool in the background. At some point, we're going to go ahead and get the result. So at some point, we're like, I can't wait any longer. I need to get this result. And in that case, we will either call the get method, which will block until the computation is done if it's not already done. If it's already done, you get it right back. If it's not already done, it blocks until we get it back. Or we could do a polling or timed block where we could say, wait for up to this amount of time. So that's a quick overview showing how to program with classic Java futures. What we're going to do next, of course, is talk about the pros and cons of this approach, so you'll understand why we have Java completable futures to work around the downsides with Java futures. So the last thing we're going to do today is talk about the pros and cons of Java futures. And you'll see that it has a few benefits, but there's also a lot of limitations. So the good aspect of futures is it allows you to potentially leverage greater parallelism available on the platform while using fewer threads. So you don't have to have a thread for every call. Instead, you can have a fixed size pool of threads. And what you can do here is you can essentially queue up the asynchronous computations for execution in a pool of threads, which could be fixed or variable. It all depends on how you want to set your system up. So you submit the work, and the number of threads can be automatically tuned. You could keep it fixed, you could grow them, and so on and so forth. And then the results can be taken from the queue of completed futures. So assuming we've kept a queue of these things, as would be the case with, say, the executor completion service, which is a really cool framework that's part of the Java executor framework in Java 5. Then what you can do here is you can go and block waiting for results to show up on this completion queue. And when the results show up, then you can get them and do something with them. So it turns out that calling take on this completion queue will block if there's nothing there. But after you get something back, which is a future, the get call will always return immediately because it wouldn't have shown up in the queue unless it was completed. So another nice thing is you can block if you want to until the results of an asynchronous two-way task is available. And you can either do that in a block forever kind of way, or you can do it in a poll or time blocked kind of way. So those are the pros. Another thing you can do, of course, is you can check to see if something's done, and or you can check to see if something's canceled. And if you want it to be canceled, you can cancel it. So there's a bunch of different things you can do to control the life cycle of tasks that are submitted to run asynchronously via the future proxy that's returned when you submit the task to run asynchronously. But of course, not everything is rainbows and unicorns. And so there's actually some serious limitations with Java futures. And the biggest problem is that it just doesn't give you a lot of capability. It's very limited in terms of what it does for you. Here are some things that are not provided by Java futures that are actually very important to have if you want to do true asynchronous programming. So one thing that you can't do is you can't complete a future explicitly. There's no API on the future interface to complete it. And instead, you have to use other mechanisms like future task, which is another way of handling things in the Java 5 executor framework context. You can also not chain together the results of Java futures fluently. So remember, we've been talking a lot about fluent interfaces, and we talked about fluent interfaces in the context of Java streams and Java parallel streams and so on. You can't use fluent interfaces to chain together dependent actions to handle the results of asynchronous processing. It just doesn't work with Java futures. Something else you can't do with Java futures is you can't trigger them reactively. You have to poll or wait on them, or do a timed wait or a timed poll on them. And so as a consequence, it just gets more awkward. And using timeouts with futures is almost always the wrong thing to do, because how do you figure out how long to time out? How long do you figure out how to wait? So that's another problem. And then yet another problem with futures, another limitation with futures, is you can't treat them efficiently as a collection of futures. So here's how this turns out to be a problem in practice. Imagine that we go ahead and we start up a couple of different futures. So here we're going to have future 1. We're going to submit some computation with the common fork join pool. Then we also, in parallel, submit another computation to run in the common fork join pool. So now we have future 1 and we have future 2. We can't easily write code that says, I don't care which one finishes first. I want the first result. You have to explicitly wait for those futures in some order. You wait for future 1 first. You wait for future 2 first. Almost invariably, no matter which order you wait for them to finish, it'll be the wrong order in some circumstance. Either future 1 will take longer to complete if you wait for it first, or if you wait for future 2 to complete, future 1 will complete first. So it gets really complicated, and putting in timeouts makes things even worse. So it just gets really awkward and doesn't scale. So the bottom line is it's awkward and inefficient to try to compose multiple futures together. It's like trying to put a square peg in a round hole, or trying to fit puzzle pieces together that don't actually fit together. These limitations with traditional Java futures, what I sometimes call classic futures, motivate the need for the Java completable futures framework. And so we're going to talk, when we come back next time, about all the different capabilities that are provided with Java completable futures that overcome these frustrating limitations with classic Java futures.